Hello everybody, and welcome to this webinar on quantification of steels and alloys using a dual source multi-detector system. Part 2, SEM-WDS, adding to XRF-EDS and SEM-EDS analysis. My name is Andrew Menzies, and I am a Senior Application Scientist for Geology and Mining at Bruker Nanoanalytics in Berlin. I'll be the host and presenter for this session. Before we start, let me give you some housekeeping details. You should at this time see the introductory slide on your screen. This webinar is interactive. You can ask questions at any time during the presentation by entering your question in the according box on the right side of your screen and sending them to us. The presentation will last approximately 40 minutes, and after the presentation, I will present your questions to our speakers. If we are not able to get to your questions during the live event, we will follow up with you by email. And for your information, this webinar is also being recorded and will be available as an on-demand version very soon. As I said, my name is Andrew Menzies, and I studied geology at the University of Cape Town in South Africa, after which I worked as a geologist for mineral services responsible for both field and laboratory work in the diamond industry. After this, I moved to Intellection Australia, where I worked as a project specialist for automated mineralogy development. And in 2009, I joined Universidad Católica del Norte in Chile as a professor of geochemistry and managed the analytical facility in this department. I joined Bruker in 2018 as a senior application scientist. The other presenter is my colleague Michael Bratis. Michael studied geology at the universities of Kiel and Göttingen, where he also acquired his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michael built up and managed a microprobe lab at the University of Jena before he joined Bruker Nanoanalytics as a senior application scientist for WDS in 2015. So now let's get started. So this is part 2 of a presentation on the quantification of steels and alloys. We'll be focusing on the WDS component and what it brings to the ability to quantify various elements. As an introduction and overview, the first part of this webinar was presented approximately a month or so ago and is available through the Bruker website. In this part, we looked at how to analyze samples using a dual beam source, i.e. an electron source and X-ray source, and how they interact and the benefits that each of those bring. The detector used for that was EDS. So we were talking about the benefits of electron analysis with EDS and X-ray analysis with EDS. Today now we'll expand that and include WDS and what benefits it can bring to an analysis. Now, this incorporated various components, and we'll be talking about multi-method approach for quantification and how this adds to the overall ability to detect minor and trace elements and specific elements within steels and alloys. So what is the motivation for a multi-method approach? Well, here we can see that there is benefits to each of the different types of methods of analysis. And we've applied this to the quantification of steels and alloys because they can be problematic due to the various elements of interest, ranging from very low Z numbers up to high Z elements, and with concentrations from majors, minors, and traces. So E-beam excitation with EDS has very good low Z element sensitivity and spatial resolution, but it has a relatively high spectral background and limiting sensitivity. X-ray excitation, on the other hand, has a low spectral background and thus has high sensitivity for high Z elements. However, it has a limiting in spatial resolution and light element detection. And today we'll talk about E-beam excitation with the WDS detection because it has high spectral resolution and improved peak background ratio, especially compared to E-beam EDS. However, one of its limits is it's a sequential analysis. So more about that later. Here we can see an image of the system that was used for these analyses. You can see here that the dual source excitation with the SEM and the electron beam column, and on the right is a X-ray beam source at an inclined port. And there are two detectors, the EDS, which is partly hidden from view on the left-hand side at the back, And today we'll be talking in more detail about the WDS, which is shown here in the white circle on this image at the back of the SEM. So as a review, in the last webinar, we analyzed a range of steels, and this will be described again shortly. And here is just an example of some of the results. Here we can see the micro XRF was able to present results for minor and trace elements, especially for the heavier Z elements from titanium onwards. The SEM-EDS could do the major elements of some of these elements, but was unable to do trace element levels, and was able to do silica as a lighter element, but for minor concentrations. And now we'll be focusing on WDS and how it can help with some of these other light elements and low level at low level concentrations. So the analysis of steels and alloys and the benefits and why it's useful for combined quantification. And this is because, as mentioned, there are a range of benefits to each of the electron and X-ray excitation available. That is better light element sensitivity with electron excitation from carbon to silica, and better trace element sensitivity for heavier elements such as X-ray generation. So now we're going to talk about that, but now with the perspective of including SEM-WDS and how that augments and combines with the aforementioned analyses types and what benefits it'll bring to the system. As a brief introduction, we see here the WDS component on a SEM, a schematic of the SEM. The QUANTAX WDS is a part of the QUANTAX family of SEM-based microanalysis. The XSense spectrometer is a so-called parallel beam spectrometer with a grazing incidence optic, and the QUANTAX WDS is fully integrated into the software package. So this webinar will now introduce further information about the WDS and its quantification benefits. So now I will hand over to my colleague, Michael, and he will continue from here.
So thank you very much, Andrew, and hello everybody. I'm Michael. I hope you can hear me all. So the question is, why should we use WDS and SEM for the analysis of steel? And here are at least 4 arguments I will present. They are related to the strengths of WDS technology. The first one is WDS has a very high peak to background ratio, which leads to low detection limits, especially for the low atomic number elements. That's why we can contribute with good analysis for traces of aluminum, silicon, phosphorus, and sulfur. The other strength, especially of our WDS, the XSense, is the high sensitivity for light elements. And therefore, we can analyze the light elements nitrogen and carbon in steel. Third argument is the high peak resolution, the intrinsic feature of WDS technology. So spectral resolution of the WDS is up to 20 times higher than that of EDS. So we can resolve overlaps of tungsten M lines with the silicon K lines, or for example, also molybdenum L lines from sulfur K lines. And fourth argument is we have a very high spatial resolution, like other E-beam technology, so EDS as well. So it's the same on the same scale, and that is better, so higher resolution in terms of space than X-ray based technologies. So we can see heterogeneities if there are. We analyzed steel sets, 2 steel sets. One is the Army steel set from the Analytical Reference Materials International, and the other one is ACX, the ASA Inox set of samples. So both contain 15 chrome nickel steels with certified compositions, a variable content of both have a large spread of major and trace elements, and yeah, we use these two sets of samples here, well defined. They, for example, the Army steel set is here are some data on the spread of contents. Major elements for both sets are clearly chromium, iron, nickel, and also manganese for most of the steels. Minor elements, they contain light elements such as carbon and nitrogen, and metals like aluminum, metalloids like silicon, non-metals like phosphorus, sulfur, and a lot of transition metals from titanium to tungsten. The composition shows a widespread, and that's why it's also challenging. It starts with tens of percent and goes down to tens of ppm in concentration. WDS can in principle determine all the elements. So we can also determine the major elements such as chromium, iron, nickel in the steels. But since this WDS is designed for highest efficiency and the low X-ray energy, we have to concentrate here on the L lines, which is not a great deal. We can do the quantification with the L lines also. We recommend to use similar composition samples as standards, but we could then quantify the major elements, but we didn't in this case because we go for a combined quantification, and we have other techniques such as EDS or especially micro XRF, which well determine the major element compositions. So it's not worth it measuring it with WDS, since WDS is energy selective and we have to acquire a reference material also. So that means a lot of time. So we concentrate more on the trace elements. That's the real challenge. And that's the strength also of WDS. WDS has a high peak resolution, higher peak resolution than EDS, and shows high peak to background ratios for the characteristic X-ray lines. So that means low detection limits, and especially for the lower energy range from about 3 kV or 2 kV. In that range, that's the transition from micro XRF to WDS. So spending some time here on the analysis on trace elements of the lower Z numbers, this is really worth it. So there are two different modes of acquisition with the WDS. It's energy selective, so we measure one energy after the other, and we can scan across a range of energies with help of the energy range scans. So we see that on the left-hand side of the image, we see here the nice sharp peaks here of WDS for silicon and for phosphorus, and in the background there's the EDS spectra, the section of the spectrum. We see that WDS has a much higher peak resolution and a much higher peak to background ratio. That is obvious. On the right-hand side, we see the second acquisition mode. This is peak to background measurement. So we are just measuring 3 points, one on the top of the peak of the element, and two positions to either side of this peak to determine the background. This is what is needed for a quantitative measurement, and this is much faster, clearly. So we can spend all the time on just 3 points instead of scanning or spending all the time on all the points with a range scan. So how do we do the quantification? For WDS, it's essentially standard-based. So WDS is not an absolute method. It needs comparison with standards, with reference material, and to get some concentration. So we go like this. We determine first the net intensities of the unknown sample, and then we compare these net intensities with some reference material, so-called standards. From the reference material, we know the concentration, and we determine the net intensities under the same conditions like we do in the measurements on the unknown sample. So same conditions means we need the same geometry, and we need the same acceleration voltage. And the third parameter that we have to record, it could be different between sample and standard, but we have to record because it's a factor that has a great effect on the net intensity. That is the beam current value. So we have to measure the beam current with a reference sample or directly with the Faraday cap. And then for sure we have to correct for the matrix effects as well. And the equation is shown here below. So we get the concentration by determining the net intensities of both standard and sample. And we apply the matrix effects for atomic number absorption and fluorescence using the phi rosette correction. So let's have a look on some of the data. Here the analysis for silicon, one of the trace elements, or in fact the composition in steel is ranging from traces up to minor elements. So we have a range of 0.2% up to 2% in the 30 steels that we measured here. Most of the compositions, so more than 80%, are clearly below, on the lower end, so below 0.6 weight%, but the range is large. We see here a nice correlation between the measured values and the accepted values, so it's well on the one-to-one line, or just not going further than about 10% deviation from this one-to-one line. So the analysis is accurate and precise with WDS. So it's on the analytical conditions. We applied a high acceleration voltage and a high beam current, 20 kV, 17 nanoampere, to get a good high count rates. So to be somewhat fast, we could do the same measurements with just lower kV for better spatial resolution and also lower beam current, but that would mean longer acquisition time to get some good statistics. So when we compare the data with EDS, we see here on the left side this what we've seen before, but with a focus on the lower end. So we see only the concentrations below 0.8 weight%. So the nice correlation. So measured values are matching well the certified values. And on the right hand we see EDS. EDS can well determine silicon, but there is more scattering. So the precision is not as good as with WDS. So I have to state here, or to emphasize that the conditions were the same. So the measurement time were 300 seconds in each time. So that's not the question here. So we allowed the same time. And actually for EDS, it was optimized also for best conditions. So best throughput with maximum shaping times and finest processes. So why could determination of silicon be somewhat tricky? Why is it a challenge? And this is because there could be an overlap with the tungsten. So silicon K alpha is very close to the tungsten M lines. So in fact, the difference between the two line positions is just 35 electron volts, and that's too close for EDS resolution. Keep in mind that an EDS has a resolution at this energy range of about 70 electron volts, whereas the WDS has a resolution of 3.5 electron volts, so a factor of 20. So clearly the WDS can better resolve these two peaks here, silicon and tungsten. What we see here is a range scan across one of the steel standards here, ISI 422. And this one contains 1% of tungsten and some silicon, and we can nicely resolve these two peaks. EDS has has a nice feature, a nice software option, which is oops, somehow lost my connection here, which is the peak deconvolution. I get some problems with my screen here. Okay, so but I hope it's all okay for you. So peak deconvolution can sort out the two peaks when concentration is high enough and the peaks are when there's not a large difference in intensity between the peaks. So in many instances we can deconvolve the two peaks of silicon and tungsten, but it gets very difficult when concentrations are so low, like we see here. Now we get to a real trace element. So phosphorus and steel is present in very low concentration, so a few hundred ppm only. You see the range here in the stand is 140 to 400 ppm. So that's a real trace element. That's very low, and that's actually beyond what we expect from an EDS, beyond the detection limit of an EDS. I still try to measure the phosphorus content by EDS. I forced it to see something, but as you see here with the open circles, EDS is not determining well the phosphorus, but WDS with the solid points is determining phosphorus well. So there's a good correlation between the measured values and the accepted values. Yeah, so phosphorus, even in that low concentration, is of high interest for the steel industry. So if you want to determine it, use the WDS. Another element, molybdenum, a transition metal, that is actually well determined by micro XRF. It could also be determined by WDS, so it takes much more time. So we would recommend the micro XRF, but it could be determined by WDS as well. Not on the K line, which is above 17 kV. So we are using the L line at 2.3 kV, and you see even that is nicely determined. So we have a very precise and accurate determination, like you see here. And why is molybdenum of interest? Why do I show this here? And we see here the overlap between molybdenum and sulfur. These lines are very close, only 14 electron volts apart from each other. And WDS can resolve this. So we see here a scan across an energy range scan across the energy range encompassing the molybdenum L line and the sulfur K line. A scan on one of the steel standards, AISI 416, with a molybdenum content of 0.08 weight% and roughly 0.3 weight% sulfur, and we can nicely resolve, WDS nicely resolves the peaks for both elements. So we can measure both. That's what we've done here. We see some results on the sulfur. Most of the determinations, they match the accepted values, like you see here. It's quite close to the one-to-one line between measured values and accepted values, but there are actually some deviations. So some of the analyses go up to apparently high sulfur values, which are just related to high molybdenum contents. So where we see 2% of molybdenum or more, like what is typical for the high for the V4A steels, so the molybdenum-rich steels. So in that instance, high molybdenum, low sulfur, that is tricky. There we have still the overlap, so that's even somewhat a limit for the WDS. And then let's get finally to some light elements. A nice feature of the X-Sense, it's the high sensitivity for light elements such as nitrogen in this case. So nitrogen in steel shows concentrations from 100 ppm only up to 0.3%. Most of the samples have, so more than about 80% have concentrations below 600 ppm. And still we see we can measure them. The precision is somewhat poor with this multi-layer crystal, with this diffraction element that we use, the 60 angstrom crystal here, 60 angstrom multi-layer, I should say, because this multi-layer has a low sensitivity in this energy range. It's more, it's built for higher energies, ranging from 500 to 700 electron volts. So for determination of oxygen and ion lines, it's a perfect multi-layer, but not so good for the nitrogen. This is because of the low peak to background ratios. So we have some scatter, and this would require long measurement time. And at the left-hand side, you see the conditions. I didn't take much time. I just measured them for 60 seconds. This was obviously not enough to get some precise data, but I was somewhat impatient. So the conditions are 4 kilovolts to get a higher resolution. It was sufficient, and 20 nanoamperes. So this is what we can apply as well. Low kV, also lower beam current, but the lower the beam current, the longer the measurement time. So we have a different crystal for measuring the nitrogen. So our second option is taking the 80 angstrom multi-layer, which has a much higher sensitivity. Sensitivity is 10 times higher than the sensitivity of the other multi-layer for this energy range. Yeah, so this has to be emphasized. All the crystals and multi-layer have a specific energy range where they are designed for. So the data that we get here is much more precise. We see a very quite good correlation here. R factor 0.97. So that's a good correlation for the data set here of the Acer inox steel samples. However, we clearly see this offset. So the data is offset from the one-to-one line, and we puzzled sometime for the reason. And the reason is actually this multi-layer is composed of chrome scandium, and the scandium shows some secondary fluorescence here when analyzing ion-containing materials and so stuff like this. So we have this background offset, but we can correct for this offset with an offline correction. And that's an easy calculation. And then after correction, then we get not only precise, but also accurate data for nitrogen down to concentrations of only 100 ppm. So here comparison with the EDS results. So EDS is not sensitive. Normally EDS is not sensitive for these light energies. So we see zero contents. Only the higher concentration there we have some indication for nitrogen, but the errors are large. Yeah. So take the WDS for determination of light elements. Yeah, for most of the light elements, also carbon could be determined very well in principles to at least 0.1% or below. But the problem is contamination, and SEM is everywhere. And this is what we see here. We see in this graph again correlation of the measured and accepted values, and we see correlation for some of the analysis for the higher, for those steels that contained higher amounts of carbon. Then we see a nice correlation. However, for the low carbon steels, we see some background, a system blank that does not allow us to get below 0.3 weight % at the moment. And the system blank is to contamination not only of the sample, so we have to clean them thoroughly. And if you are interested in determining the carbon content at the very low end, so you should use plasma cleaner for sure. You should make sure that your SEM is very clean, that you do not use carbon pads, do not use tapes. Make sure not to use the door, but an airlock system to insert your sample. Clean the interior very thoroughly and use the plasma cleaner steadily, and also use an air jet to blow away the carbon on the analysis spot and freeze out the carbon with help of a cooling finger. And this is what we will do at some time in the future. And then we will present better data where we show the WDS can in principle go much lower to very low carbon contents. The limitation is just here the system, the contamination of the system. Yeah, contamination during analysis, this is what you probably know, all of you, unless you are very, very careful from the very beginning. Never insert some carbon containing material, never make sure not to get hydrocarbons into your chamber that can be cracked under the electron beam. So what we see here is the scanning areas for where we did beam scan across the field. So we see the rectangles, and we also see the beam spot where we did some point analysis with a ring of carbon. So there is carbon deposition instantaneously due to cracking of hydrocarbons in the chamber atmosphere and deposition of the carbon dust. So this is what it looks like. So I acquired some range scans for the carbon on steel. On the left-hand side, you see the range scans over time. And you see the increase of this carbon peak. So with analysis time, you will determine more and more carbon in your sample. So the peak gets higher and higher over time. So this seems to be quite a long time, 30 minutes, but you get the increase instantaneously. So we can see that increase on the right-hand side in that graph. Also, I did some quantification over time and did some peak background measurements instantaneously. As soon as I got on the spot, I always acquired for for 60 seconds on the peak and another 60 seconds for background measurements, so 2 minutes. Is what is shown here in this graph. So the longer we acquire, so I acquired on the same spot a continuous series, and we see this apparent increase or this actual increase because of carbon deposition, and we can follow this trend line back to the initial state, and we will get out here at somewhat like 0.2 weight % at which is the initial carbon that we measure. And what we in fact measured was something like 0.36 weight %, and we ended up and after 20 minutes at 1.2 weight % carbon on the same spot. Yeah, some more carbon here. We used mapping by WDS, and that's great. Also, we can map the heterogeneities of carbon distribution in the samples, and there are actually some heterogeneity. Standards should be homogeneous, but homogeneity is always a question of scale. So with X-rays, with the micro XRF, we didn't see that because the analytical volume is larger. We clearly didn't see the carbon, but we could also see the chromium variation, but this small scale heterogeneity can only be resolved by electron beam. And we see here on the left hand side a sample with chromium carbides, the green spots. They are rich in carbon, but also in chromium, and we mapped here the carbon just for something like 5 minutes. We mapped the carbon and the iron in the background, so we see some carbon chromium carbide inclusions in this steels. So WDS is very good also for spatial resolution. On the right-hand side, we see something similar, or two different phases. It's a dual phase steel containing martensite and ferrite. And we see the differences in carbon contents between martensite and ferrite. And this, though the absolute contents are very low. So martensite only contains 0.3 weight% of carbon, whereas ferrite contains 0.01% of carbon. So determination of absolute concentration is still somewhat tricky due to the contamination, but mapping the differences is an easy task. So let's get back to quantification. How did we do the combined quantification to get the best of all the three techniques? So here's a sketch showing the sequence of quantification. So we started with some EDS determinations. This is shown here, the list of elements which might all be present in the steels determined by EDS. And what we show here in green, these are elements that can be well determined by EDS, which is, for example, silicon and the major elements, chromium, manganese, iron, and nickel. And there are some greenish striped regions like aluminum, titanium, vanadium, cobalt, and the transition metals, which can be determined by EDS when concentration is high enough. So it depends on the concentration. So this was our initial value, and this was the basis for micro XRF. We then determined the transition metals with micro XRF, and we got good data, like what is shown here in green, from titanium down to at 4.5 keV, down to the molybdenum at 17.4 keV. So we could well determine all these elements, the transition metals from major to traces with micro XRF. And the basis was the EDS, and then the final determination XRF. It's an iterative process. And at the end, we also get some improvements for the EDS data when these values are inserted in the combined quantification. For WDS, we also use a combination. We are measuring both at the same time, EDS and WDS. So we get some data at the same time. For WDS, we get the low Z numbers, is shown in green here, and blue is what we cannot get nicely, or what we leave for better methods like the micro XRF. And these data, the initial data, will then be refined by hard coding or inserting the micro XRF data, which got the best results for the transition metals, and then the analysis was recalculated, and we get the final compositions with best values for the low Z elements by WDS, best determination for the higher Z elements by micro XRF in combination with EDS. So, and this combination will be the final results, and it's shown here with some numbers where we determine sequentially the values by combining the strengths of all three analysis types. And here are some results for just two of the samples showing the light elements and the low Z elements determined by WDS. We also get some nice numbers for copper and molybdenum, but we have these data from micro XRF, so the transition metals. We also have the EDS data for some higher concentrated elements, and then we get to the combined quantification for these two steel types. Here's another steel AISI 347, and we see the combined analysis gives good results which well match the certified values, maybe except for the carbon, which shows the high system blank here still. So here we are at the end of the talk already. That's a summary here for the WDS benefits. Why did we use WDS in this combined analysis? Because of the high spectral resolution potential. So we could resolve severe EDS peak overlaps like silicon tungsten, molybdenum, sulfur. We also get high peak to background ratios that lead to low detection limits, especially for the low Z elements like aluminum, silicon, phosphorus. And second point, we have a high performance for the low X-ray energies that allows us analysis of the light elements also, carbon and nitrogen, and gives good trace element contents for the low Z elements where the micro XRF cannot or has a lower efficiency. Third point, the high spatial resolution with an electron beam that is higher than a resolution with a photon beam. So this allows analysis of sub-micrometer structures, like for example the carbides that we saw, and due to the full performance of the WDS also for low kV, we could make use of this. So we can do analysis starting with very low kV, and we get good results even at low kV. And at this point, I will hand over to my colleague Andrew again, and he will give the summary of. Sorry.
Okay, thank you very much, Michael, for that detailed and an excellent description of WDS and how it can help with quantification, especially in complex samples that have a range of concentrations and various elements from the very light end, from carbon through to heavier elements. So just in summary, we see here that there are benefits to employing in one system either an X-ray or an electron excitation, and having the two different types of detectors, an EDS or a WDS. So the electron excitation is preferable for light elements because of its intensity of the signal that it will receive, and this is either for EDS or WDS with the benefits of each, especially as described by Michael in this presentation. X-ray excitation is preferable for the heavier elements and for trace levels of those elements, especially given its low background compared to electron excitation. And it must be mentioned in these cases, samples can be analyzed and quantified either as spot point analyses or from hypermaps. As was mentioned, the X-ray beam is larger than an electron beam, so the resolution is larger. So any fine scale variation or inhomogeneity will be averaged out, and that's where perhaps electron excitation is going to be useful if there is variation in your sample or potential variation to confirm that. And so in summary, there are benefits to each of these different techniques, from micro XRF, electron beam, and combining it with an EDS or WDS to get your best concentration results. So with that, we'll finish the webinar and move on to some questions. Thank you for attending. And prior to just starting with the questions, just to mention that if you'd like to learn more information about any of the systems we've mentioned today, there are other webinars detailing specifics of the techniques and also the first part of this quantification webinar. So those can be found via the Bruker website, where there'll be presentations and videos of the various webinars. So let's move on to some of the questions. So a question that's come through is, Michael, so I think this one's for you. What is the operating kV required for WDS analysis and accurate quantification?
Yeah, so there is no required kV. So from the WDS perspective, yeah, with the kV you have to respect the overvoltage ratio. So make sure that you excite the X-ray line you are interested in. So use a kV that is double that of the binding energy, and so that's what is required from regarding the element or the X-ray line for investigation. On the other hand, the kV has an influence on the analytical volume. So the higher the acceleration voltage, the worse your resolution, your spatial resolution will get. So because you get a higher excitation volume. But the advantage is that you get a higher signal also. You have a higher volume excited, so you get more counts from this larger volume. So that's why I applied 20 kV for many of the trace element analysis to get a higher signal. But in principle, we can do the analysis with very low kV, also with 2 kVs, for example, especially for the very low X-ray energy. So for the light elements, in this example, I used 4 kV, but we can also go lower. But lower kV means better spatial resolution, but also lower signal. So you have to count for longer time.
Okay, thanks, Michael. And I guess a follow-up to that in relation to kV and what you just mentioned there is what are typical acquisition times that were used for your data collection in these examples?
Acquisition times, they depend on the statistic that you want to. So the longer you acquire, the better the statistic will be. So because that means more counts, and more counts means better statistic. But so I checked for the sigma value and to get it low to the statistical error, to get it somewhat below 10%. Otherwise, it's a rule of thumb, just taking some values, like for major elements, I often apply 30 seconds on the peak measurement. And for trace elements, I applied 200 seconds on the peak. In this case, I also used 300 seconds to get very good values. So it's quite some long measurement time to get good statistic, good and precise results. But at the end, so for EDS, for good analysis, it also takes time. So you just get a first idea with a very quick analysis, but for precise analysis, you need time.
Yes, I guess an extra comment related to that is this is where the benefit of combining all the systems can come in, because WDS is a sequential system. You have to analyze each element individually, whereas with the micro XRF-EDS or SEM-EDS, that is simultaneous. And therefore, if there are certain elements, say like the higher energy elements that could be done by WDS, you may end up taking a long time by analyzing them individually. So if you have access with the combined system, you can prioritize your most important elements and to be conscious of the total analytical time required.
Yeah, definitely. That's a good point. Yeah. So that's why we apply the WDS just as an add-on or a good method to for the analysis of some elements, traces or light elements that cannot be determined by the other techniques. So, but we get the other elements at the same time much faster with different techniques like EDS or micro XRF. So combination is actually the best, and it's possible.
Yep.
Yeah.
Yep. Exactly. I mean, and that's why, you know, the purpose of this presentation to show that you get that full range from carbon, from the light elements to the higher elements, and then the objective is to maximize the potential of that. So another question here related to standards. I guess this is a two-part question. What standards did you use? And there's a follow-up question is, that was for WDS, but when combined with EDS and XRF, do you need to use standards for all the techniques and all the, for all techniques and all elements?
For WDS, we need standards. Yeah, it's the only way to quantify. So qualitative, just a range scan, we don't need standards, but to get some numbers, some concentrations, we need standards. There is no way for a standardless quantification. But for the other techniques, we don't need standards, and we can combine that in a combined quantification. It's not a problem to combine standard-based WDS and standardless EDS or standardless micro XRF. So that's no problem at all with the S3. And what kind of standards I used? So normally it's a good advice to use standards that match the sample composition very well. So take some standards that use steel for steel analysis. So this is in many cases a good advice, since with that rule so the matrix correction effects, they will be cancelled out. So if you're using the same, but for trace elements like the metals here, so aluminum, silicon, or metalloids, molybdenum, copper, and so on, I could use pure metals, pure elements. So trace elements, it's not a problem. For the nitrogen, it turned out that we had to use some metallic components. So for the nitrogen, I was using a steel with highest concentration. But for the other traces, I could use pure elements. So for trace elements, it's okay. For major elements, I would strongly recommend to use similar compositions to get down effects from matrix correction.
Okay, and one final question I see here, and that's about sample preparation. What are the requirements for WDS analysis with respect to sample preparation, especially in relation to quantification?
Yeah. For quantification, we have to make sure that the same conditions with sample and standards, so the same geometry, like I said. So that means we cannot use a rough surface. With the rough surface, we have scattering of the X-rays and absorption. So that it's important to have a flat and well polished sample for quantification. Yeah, that's a prerequisite, and otherwise, coating is not necessary when the material is conductive. So for steel, we measured uncoated samples, especially when we try to quantify the carbon.
Yes, I guess that's quite critical there. If carbon is of interest and your sample's conductive, there's no benefit to applying a coating.
Yeah, the correction is very difficult.
Yes, exactly. And I guess one final comment on that. We are talking about a combined system, and one of the potential or one of the benefits from a micro X analysis is that the sample doesn't have to be polished to the same level as, say, a WDS or for an SEM-EDS analysis, given the beam size and interaction volume. However, if you are planning to do a combined analysis, as we presented here, then yes, you would want to make sure that your samples are prepared for what is the requirement for all three analyses, since that'll be important. So in that sense, having a higher end quality polish, while not necessary for micro XRF analysis, will be necessary for the EDS and the WDS analysis. Okay, well, that's the end of the presentation. Thank you very much for joining us.
Yeah, thank you.
And so a quick reminder to our viewers, you can submit some more questions if needed, and we'll be able to get to those. For those questions that we haven't been able to answer, we will contact you via email. And this presentation has been recorded and will be available on the Bruker website shortly. So thanks again to my colleague Michael, and thank you for being with us, and we hope to see you again in future webinars.
Yes,
Thanks
thank
a lot.
you, Andrew,
Goodbye.
and thank you, the audience. Goodbye.
Goodbye.